What you see in this first transparency is a Roman mosaic pavement. This is an example of something which is very definitely designed. But we're going to ask about whether the same idea about design can apply to the universe. Let me try to define one or two words. What do we mean by design? We mean the application of a mental idea to the construction of some physical system. And if there is design, there has to be an idea somewhere. And we have to have an agent to apply it, and probably there is a purpose behind the design. So there's a cluster of concepts that are associated with the word design. We understand how these concepts apply if we're talking about human beings and things that human beings design. We recognize design because we can see structure and pattern and coincidence in the object which is designed. If we don't have design, you have, well, randomness. Now, let's consider something which certainly looks very regular. Let's consider a salt crystal, sodium chloride. Now, that certainly has got a pattern. It's an interesting question as to whether there's a design there or not. I won't answer that question, but I will try to list the requirements that are needed for the formation of this regularly patterned salt crystal. Your salt crystal has got to be made up of two different kinds of atom that can form ions. They must have a suitable radius. They must be fairly similar radius. There must be equal and opposite electric charges, electrostatic forces, many atoms, all of them the same, and all of this depends on the quantum mechanics of electrons and appropriate atomic nuclei for the electrons to be bound to. So you see there are quite a lot of things that have to be right before you can have a salt crystal. It's not something to be taken for granted. If you were in a completely new universe, you might or might not have salt crystals. Well, here are some people, and the question is, here we are in the universe. Does the universe show properties of design that might give rise to people? You recognize the first one and the third one. The middle one is the young Charles Darwin, just three famous people. Now, what is actually needed to have a universe that will give human beings? And we shall see that quite a lot of conditions are needed, and that it's quite surprising, perhaps, that the universe shows these conditions. Well, until recent centuries, people just assumed that it's all so obviously structured and let us even say intelligent, that God must have just imposed designs on everything. You have a chicken, God designed the chicken. But now we need an approach that fully takes science into account. Now, there was a big breakthrough in thinking about this whole area in 1973 when someone called Brandon Carter invented, or at least realized, that there was a certain principle that had to be applied. We call it the Anthropic Principle, and it's actually quite common sense. The universe must be suitable for humans, or else we could not be here to analyze the universe. But is it likely that the universe should be suitable for humans? That's the big question. Anthropic means to do with human beings, of course. And there's a classic book that was put out in 1986 by John Barrow, who lives in Cambridge, and Frank Tipler, who lives in America, The Anthropic Cosmological Principle. It's a classic book. You can buy it. It's quite difficult reading. You have to know quite a lot of physics to understand this book, but they spell out everything. Things have updated since then, but that's the classic. Now, if you want an easier book to read, one by the former Astronomer Royal in Britain, Martin Rees, called Just Six Numbers, can certainly be recommended. And he explains in simple terms what Barrow and Tipler explain more complicatedly. But the fact is that certain physical constants in nature must be more or less right. If they're not right, we wouldn't be here. And Martin Rees says there are just 6 numbers. That's slightly an oversimplification, but it's good enough for now. Now, I'm going to give you a list of the believed necessary conditions, or at least most of them. Then I will go through them in detail. Then I will discuss the implications. And this will be a little bit technical, but I want you just to understand the general ideas, and don't worry that you have to understand every detail. But if I don't give you the details, you might wonder what I'm talking about. So I have to show you that the details at least exist. Now, what do we need? Well, there's some basic things. We need space and time. Time I won't talk about, but space needs to have 3 dimensions. Now, you might say we're quite used to that. Why 3 dimensions? Actually, this is absolutely necessary. If there were only 2, there wouldn't be enough sort of room for things to be in it. It would be very, very limiting. If there were more than 3 dimensions, surprisingly, orbits of planets around the stars would not be stable. This can be worked out by physicists. You can do these calculations in multiple dimensions. Only 3 dimensions will do, and 3 dimensions is what we have. Now, there are 4 kinds of force that exist in physics. I need to tell you a little bit about these, but I'll try not to make it too difficult. There's a force that binds protons and neutrons into atomic nuclei. This is the so-called strong nuclear force. That's got to be right, as we shall see. The electromagnetic force binds electrons with nuclei to form atoms. Well, we are made of atoms, so that's got to be right. Now, there's something called the weak nuclear force, which, among other things, is responsible for radioactive decay of many unstable atoms. That also has to be roughly right. And gravity holds stars together. Now, that's got to be right too. So I'll talk a little bit more later about these, but these 4 kinds of force you should try to remember if you can, because I shall come back to them. Well, elementary particles. Now, this is a big, big subject. And what I've done here is just give you a sort of pictorial table of the basic elementary particles that exist, at least those we know about. You do not have to understand all of this, but what you can see is there's a set of particles called quarks. Notice that there are 3 sets of 2, ranged like this. And the ones that we are actually made of ourselves are called U and D. That's up and down. That's just a name. There are photons, particles of light. Gluons hold the quarks together. There are some rather more mysterious neutral particles called neutrinos. They come off when a lot of radioactive particles decay. There's the electron. Here are 2 more heavy electrons. You needn't worry about them. And there are other particles that carry the weak force. Again, so this is a quantum effect. A famous Higgs particle, so-called God particle, plays a big big part in this field. I won't talk about that one again. But this is a mathematically complex and subtle scheme. And all of this is there, and it gives rise to many, many possibilities of how matter can exist and form things like atoms. Now, here's a list of some major requirements for a universe for human life. So I've just mentioned some basics. We're now getting a bit more specific. Now, we're made of protons and neutrons and electrons, not made of antiprotons or antineutrons or anti-electrons. You must have a universe that has got a lot more, let us say, matter than antimatter. Otherwise, everything would annihilate each other and nothing would be stable. So that's a requirement. It's got to be a long-lived universe. We shall see a bit about that later. Galaxies must form. Hydrogen must form in the right way. Helium, the next element up, that's got to be there. Ability to form heavier elements in stars, that's got to be there because that's what we are made of. The first stars must explode properly. I have to talk a bit about this one. As the universe developed, first of all, there was a generation of really large, powerful stars that are all gone now. But they went because they exploded and gave off a lot of matter with heavier elements, which then formed the next lot of stars. Our sun is one of the second generation of stars. So you must remember that there are 2 generations of stars in the history of the universe. These must be suitable kinds of stars. And finally, you must have organic chemistry, carbon chemistry, because that is needed, as far as we know, for life to form. So here is a basic shopping list that you must have satisfied in order to have human beings on a planet like Earth. Let me talk a little bit more about this. You've seen some pictures of that like this from the previous talk. Now, the thing is, when everything starts up, people think that the very first universe would have to be in some sense neutral, same amounts of matter and antimatter. It's actually quite difficult to have anything that's asymmetric. Here's a photon. Now, photons can convert, when you go near matter, into positrons, anti-electrons, and electrons. Very good. That happens. But notice that you get one of each. So there's the same number of electrons as positrons. But we want a universe where there's more electrons. So where did all the positrons go? There's a bit of a mystery here, but you have to have it. Now, most production processes, as I say, produce equal amounts of matter and antimatter. How do you get an asymmetry? Now, you need to have special types of particle process to get more of one kind than the other, which is necessary. Well, I'll try not to be too complicated here, but the point is that we are made of up quarks and down quarks. I indicated these quarks. There are more of them. Why are these extra quarks there? Well, it happens, and you'll have to take my word for this, that the mathematics of all the forces requires more than just up quarks and down quarks. If only they existed, then you would probably have the same amount of matter and antimatter in the universe, and nothing much of any interest could occur. To have the mathematical freedom for all of these forces to give you more of matter than antimatter, you need to have at least 3 families of quarks. As I say, you'll have to take my word for that, but 3 families is what we find. We find we could probably use 4 or more. Actually, 3 is the number, and we certainly don't find 2 or 1. It's not understood, but this is something that just has to be right. Now, here are Martin Rees's 6 numbers. You can see it's pretty technical stuff. I'm going to refer to these numbers, but don't worry that you need to understand everything now. And as I go through this shopping list of requirements for a universe, I will refer to these numbers which Martin Rees defined. We've talked about the number of space dimensions. He forgot to mention about the number of quarks. Something to do with the density of matter in the universe. Something to do with something that Einstein invented called cosmic anti-gravity. Something to do with fluctuations in the early universe. Something to do with the strength of nuclear forces. And something to do with the relative strength of the electrical forces. So you see how all of these forces come in, and all of these numbers that Rees defines have got numbers. Just take a note that they are numbers that we know and that we can measure, and these numbers have to be right. Now, if you want to read more still, this is the best recent article that I know of, Fine-Tuning of the Universe for Intelligent Life. In other words, getting everything just right. So this is 2012. Rodney Holder's book, Big Bang, Big God, is also quite relatively readable, and you might like that. Now, I talked about one or two things. Let's talk about now the universe must be long-lived. Now, why is that? Well, it actually takes time for all these processes to occur. And the universe has to last long enough, and we have an expanding universe. It started off with a big bang, and it's been expanding ever since. This has got to happen for quite a long time, because if it all came to a stop, there wouldn't be time for the galaxies to form, for stars to form, for planets to form, and for life to develop on Earth. Now, this is non-trivial. It means that you've got to have the right kind of density of energy and matter in the universe. This is Rees's number. He calls it capital omega. And in suitable units, it's got to take the value 1. Now, if it's too high, you've got more energy and matter than you want. That would mean that the universe blows up in a big bang, and then as it expands, all this gravitating matter will start to pull it together again. And the universe will expand to a certain radius, and then it'll say, pull it together again, and it'll start to collapse. And after a while, it'll all come together. People talk about this as a big crunch. This isn't happening. This is just a calculation based on Einstein's theory of general relativity as to what a rather dense universe would do. But that we do not want. We've got to have a universe which is billions of years old. On the other hand, if the density of matter were too low, everything would fly apart very happily, but galaxies wouldn't form. It would just fly apart too quickly. You need time for galaxies to form. So this number has got to be right for the galaxies to form. And so neither of these two possibilities applies to us. Now, let's try to put some numbers into this. Now, it's been calculated that at this point in time, and we can measure omega by measuring supernovae and galaxies and various things. I won't say how we measure omega, but it can be done. It must be within about 10% of this magic value 1. And 1, just take it, it's a number that Einstein calculated. And that would mean flat space, not curved one way, not curved the other way, just sort of ordinary Euclidean flat space. We find that it's 1 to within 0.1%. So it's much better than it needs to be. At the very start of the universe, it had to be right within much bigger precision than that. It had to be right within a factor of 10 to the minus 15. Now we're talking about precision. Now, there could be an explanation. I mean, this looks as if this is a remarkable coincidence, because there's no particular reason why the amount of energy in the universe should satisfy this condition. No obvious basic reason, unless you use a new hypothesis which has been invented, something called cosmic inflation. Now, this is not the subject of this talk, but the idea is that absolutely immediately after the Big Bang, there were fields in space that made the universe suddenly blow up much faster than it's expanding now. And then it stopped. This goes by the name of cosmic inflation. One consequence of this is that it would leave you with a universe which is pretty flat. It would do this. So you say, that's good, we have an explanation. The only trouble is that cosmic inflation is controversial. It's not well understood, and it too, you just can't turn it on. There may be strong conditions that need to be fulfilled in order to have this cosmic inflation happening. So you can't just say we've obviously got an explanation. It too may need to be fine-tuned. In any case, remarkable that an inflating universe would do what we want it to do. Now, here we come back to Einstein again. Einstein produced his theory of general relativity. It's not something I'm going to talk about, but there are various mathematical constants in his equation. And one of them Einstein called the cosmological constant. It's just there in the mathematics. He invented his theory to describe gravity, and it also describes universes. But there's this extra number that you can put in, and the theory still works. So it's a physical number. What does it do? Well, it's sort of like anti-gravity. It will tend to make the universe expand. And we have measured that the universe is expanding a bit faster than you might have thought. It will probably go on expanding forever. And this is related to something called dark energy. This blue bit is the fraction of total energy, which adds up to 1, which is dark energy. The little blue bit is atoms. That's not the big fraction of the total at all. There's something called dark matter, which we don't understand either. And there's a lot of stuff called dark energy, which has been measured and dominates. It's all rather mysterious, but that's okay. It's still quite a small number, really, when you measure everything up. Now, it's non-zero, as I've said. There's a numerical value. Just take this as 10 to the minus 8 of suitable units. And if it were bigger than about 10 times this, it would be a disaster. The universe would just expand and blow up a long time ago, and we would not be here. So this anti-gravity must not be too big. Well, it must not exceed 10 times its value. You might say that's pretty tolerant, isn't it? The only trouble is that it's related to the quantum fields that you've just been hearing about. Now, in order to have, let's say, a photon that goes from A to B, you must have a sort of ground, what I call a ground state quantum field. It's part of the theory, and you make a photon by exciting this ground state quantum field, which are everywhere, into something with a bit more energy, and that pops along, and that's your photon. Now, there's a lot of this stuff in the universe. It can be measured, and I can answer questions about it later, but I won't do that now. But when you add up all the contributions from every single particle that we know about, quarks, gluons, the lot, add it all up, all the conditions that may be in, the result is enormous. There are positive contributions, there are negative contributions. And people predict a number that looks like 10 to the 112 units. It's not like what we've got. Nobody understands this. Let's say it's a bit like this. There's a big international company. It deals in millions and millions and millions of dollars. It has dollars coming in, it has dollars coming out, and it's got a bank account. Then one day, you look at how much money there is in the bank account, and you find that there's 1 cent in the bank account. How can that be? Very strange. But that's the sort of thing. We've got big positive and negative contributions to this type of energy, but the amount that's actually there seems to be tiny. We don't understand it, and people have been trying to think about this. It could be just a coincidence. It could be a remarkable coincidence, but absolutely necessary for our existence. These attempts have not been successful. Nobody can see how this can be. Somebody else, Vilenkin, a well-known cosmologist. As of now, the only viable resolution of this problem is provided by the anthropic approach. What that means is, if it weren't zero, we wouldn't be here. But why should it be so small? Not exactly zero, but why should it be so small? That's a very interesting question. Now, a bit about galaxies. Item number 3. The strength of gravity must be right. And Rees has a number here which measures the strength of energy fluctuations in the early universe. Assume that he knows what he's talking about. They come from quantum effects. And he can put a number to this. But if these initial fluctuations, we don't have a theory for this really. If they were too big, then the galaxies would be too big. Too small, you wouldn't get galaxies. This number, forgetting about the actual meaning of it in the units, has got to be right to within some factor of 10. Well, 10 to the minus 5, it could be 10 to the minus 100, it could be 10 to the plus 20. We have no idea what size it might be from natural physics, but that's the number, and it's about right. If this were not so, we would not be here. Hydrogen and heavy elements. Now, what do we need here? We need some hydrogen, but not all hydrogen, carbon, heavier elements. The strong nuclear force must be right. Martin Rees quotes a measure. That's his number. Ignore the units. The number is what you just want to look at, because if this were wrong, things would go wrong. It governs formation of deuterium, which is essential in the formation of matter, such as we're made of in stars. If it were less than 0.006, deuterium would be unstable. We wouldn't be here. For greater than 0.008, a new element, helium-2, would be possible. It doesn't exist. If it did exist, this would completely change the processes in stars, and that would make life very difficult. But actually, this number must be more precise than all that. In this first generation of stars, there are processes that make heavy elements like carbon, and carbon is very important. Now, I just indicate helium goes to beryllium, beryllium goes to carbon. Now, actually, when a famous astrophysicist, Fred Hoyle, worked this out, he could not see how it could come out, because the likelihood of these processes were too small, unless there's some excited state of carbon which would enhance the production, so-called resonance. A resonance is an excited state that will absorb energy and make the process more likely. On the other hand, if the next element is oxygen, if all the carbon turned into oxygen because oxygen had a resonance, an excited state, then it's goodbye carbon. You wouldn't have much of us. And this has got to be right to a very high precision. And it's there. This structure exists. Rees says it's got to be good to 4%, this number. A recent calculation by some people called Oberhum et al. Gives you 0.4%. If it were different to this, no, or at least not much carbon and no life. So that's remarkable. It really surprised Fred Hoyle. He was an unbeliever. He said it looks as if somebody has been monkeying around, playing around with these numbers. That's how it impressed him. Helium, we've got to have some of that. Here's hydrogen forming into helium. Two hydrogens can come together. Got to have the right amount, not too much, otherwise we wouldn't be here. We need hydrogen. Too little. Anyway, everything requires enough hydrogen, and that has to do with the decay of neutrons that exist. This is details of atomic physics, but that's something which I'm not going to try to explain, but this means that the weak force must be sufficiently strong so that you have enough. Well, this is actually deuterium, not ordinary hydrogen. So that is what forms the helium, and this deuterium, I should have called this D for deuterium rather than H for hydrogen. And if it decays before it can form helium, it's tough, but it's got to be just right. Now, these first stars have to explode properly. You might say that's easy, isn't it? But in fact, it's not. Almost anything could happen. Again, it seems to depend on the weak force. And if the weak force is too weak, people calculate there won't be an explosion. If it's too strong, the neutrinos, which are involved here, will all be absorbed in the center of the star. That's what's happened after the star has exploded. But if they're all absorbed, they don't blow off the outer layers of the star, you don't get an explosion, and it doesn't work. So this is quite a technical bit of astrophysics, but it says that the weak force has to be sort of roughly right. You've got to have the right mix of stars. You need these short-lived big stars early on. You now need longer-lived smaller stars, such as our own sun. This depends on the ratio of the electrostatic force to the gravitational force between protons. That's one measure of it. This has a number. That's a very, very big number, but that's what it comes to. Electricity is much stronger than gravitation. You can measure this. That's the number it is. If it's too small, then you just get a universe with lots and lots of small little stars, so-called red dwarf stars. They will not explode. We won't have supernovae. We won't have second-generation stars. We won't have carbon or oxygen, and we won't have us. If it's too large, you'll have lots of big blue stars, and people have decided that this won't work. It doesn't look as if you can have planets doing the right things if these blue giants are all that exist, blue giant stars. The estimate is that this number n has got to be good to about 6%. So that's fairly precise. I won't talk about chemistry because it's too complicated and we don't really know how precise all these numbers have got to be to have chemistry. But you have to bear in mind that a lot of the organic chemistry that goes on is really very precisely governed by the physics of all the chemical processes. Very hard to calculate, as I say, but I mean, what about photosynthesis? That depends critically on just one protein. Could that protein be different? We don't know, but you might well ask the question. So all of these things depend on a whole lot of complex chemical properties which we should just be aware of. I'm not going to include that in any further comment, really, but it's something to tick off as needing attention. So, conclusion so far, we don't know exactly the precision needed on all these requirements. They may not be independent of each other, but there's a general agreement that what we can see is not by chance. These are not random numbers. Everything is tied together in a very particular way, which is called fine-tuning. Now, here are some people who have commented on this. Barrow and Tipler would count as believers, and they talked about a meticulous fine-tuning. Martin Rees, he's, as has been said, he says he's an atheist. The tuning must be precise. So that's his opinion. It's not just believers, Christian believers who say this. Weinberg, anti-religion. Why is why should this cosmological constant be so fine-tuned? That's in his book, The First 3 Minutes. Hawking and Mlodinow, well, skeptics, I suppose. Most of the fundamental constants appear fine-tuned. There is a very considerable agreement that all of this is remarkable. Now, what could be the explanations? I'm going to go through the explanations that I can think of. The first is one that will occur to everyone here. The fine-tuning is naturally unlikely, but God made it happen. Perfectly logical, intelligent thing to put forward, because where you'll see that the other possibilities have problems. This is entirely reasonable from a believer's viewpoint. A creator will create with purposeful design. We assume we are part of that. And this is shown by our own relationship with God. This is intelligent design at the cosmos level. I'm not talking about intelligent design of biological processes. That's a completely different subject. So that's explanation number one. Number two, it's just luck. There's only one possible universe. There's a theory of everything, and it just works. Now, hard to evaluate this. We don't have this theory. We don't know what theories are possible. It requires extraordinary mathematical luck. You can take this as you like, but it's purely hypothetical because we just don't have this theory. Now, multiverse is the next major thing to think about. And the idea is that beyond our horizon in the universe, things are very different, or else that there are lots and lots of completely independent universes. If you've got zillions of universes, probably some fraction of them will be right for us by chance. Now, is this possible? It's a perfectly coherent theory, but it's a very extravagant theory because you're postulating a vast number of universes. Now, things about domains with different physics, I mean, cosmologists are very inventive. You can think up some kind of possibility, but it's all speculative. Superstrings are a very popular idea. These are hypothetical quantum objects that have a vast number of possible configurations. They exist in many dimensions. Most of the dimensions are hidden to us. You can curl them up and do all sorts of funny things with them. And as soon as you get to large numbers of dimensions to make the theory work, you find you've got vast numbers of different types of superstrings and vast numbers of quantum vacuums, which are the basis of everything. A number of 10 to the 500 is quoted. Now that surely sounds enough to generate almost anything you like. If some fraction of these, not necessarily 10 to the 500, but if some fraction of these were found in different universes, perhaps that would be enough to give rise to us. Well, it's a different theory to model the number of universes. It's not clear that this will work, but on the face of it, it's a plausible suggestion. Now, Roger Penrose, who you've heard of, has an objection to this. He says, our universe seems unnecessarily large for our needs. It's bigger than it has to be. Why is it so big? Well, he says, in most of the models, big universes are much rarer than smaller ones. You just have to produce a theory of universes and you can work this out, according to him. Now, a universe 1/10 the size of ours should be good enough. But he says that there are many, many more possibilities. And here's a huge number. That's his calculation. That means that what we observe is enormously unlikely compared with what might have been. This doesn't sound convincing. At least that's his argument. So he says that if this is your model, a multiverse, an incredibly rare event is being proposed for no particularly good reason. So he finds this unconvincing, quite apart from the fact that large numbers of universes is a bit of an outlandish idea anyway. Although it must be said that people like Susskind think that they like the physics so much that it has to be. Now, we can allow God to use this method to create universes. We might say the multiverse is the workshop of God. So God just creates all of these things just happening. And as soon as a universe pops up, which is just right, he says, good, I like that one. I'll look after that one. Possible. This would seem, it seems, to relieve God of the obligation to think through the requirements for a human-oriented universe. Well, perhaps that's the case, but don't forget that general laws of physics are still needed, and there's a lot of this. I mean, just think of all the physics I've described to you. You still need a lot of that. You shouldn't dumb down too much. I mean, the mathematical requirements of superstrings are formidable. People have been working, the best mathematical brains in the world have been thinking about this subject, and they're still working it out. It's a very, very difficult subject, so God must be pretty bright to invent superstrings, perhaps bright enough even just to design one universe. So what evidence is there? No evidence at all. It's just speculation. How could these ideas be tested? Nobody knows. A few ideas haven't worked. It's likely that you can't test the multiverse idea. Why then believe it? Well, it could be a philosophical argument. You think, I've got some physics which I really like, and that leads me towards a multiverse, some sort of philosophical argument. I mean, the aesthetic argument is because the mathematics is seen as elegant. It's terribly complicated, but people who go into it, there's a guy called Brian Greene you may have heard of, the elegant universe. He likes the aesthetics. In some cases, perhaps, it may be explicitly anti-religious. Don't like God, I'll have anything else. Well, this has been sold to the media. The popular journals love this sort of idea because it sells their magazines. So you can see what this says. I think that the editor of the Scientific American was being just a little bit too credulous in saying things quite the way that he said them with this particular copy. Here's Max Born, who was a quantum theorist, and he helped to develop quantum theory. I think that statement is worth mulling over, thinking about. You can certainly invent possible and impossible theories logically, but reasonableness, that's another matter. So that's a question of philosophical attitude, and there he is saying this sort of thing. Finally, there's this whole question of human specialness. I mean, why bother? Why should you think that we need to have any explanations for our existence? Why not just say, there's a universe, folks, and it went the way it went, nothing special. The cosmic tea leaves just fell this way, that's all. Don't need any explanations. Now, if you are a materialist, you might well say, well, I can't think of any real reason why we should need any explanation. We're just a phenomenon of us. Well, so forget about all that. But if you have any kind of belief in human specialist, even if it's not fully religious, then you start asking these questions. But now we're beyond materialism. The fact that we seem to be more than just physics appears to be relevant for this argument. Otherwise, you might very well suspect that you needn't worry about these things. So we could just accept that the universe looks designed for life and accept the theological consequences. I mean, as I shall say in the end, it's an entirely reasonable thing to do. You can very well say there's a lot of intelligence somehow or other in the universe, and to say that it was set up for us with the sort of people that we know ourselves to be, is an entirely reasonable thing to believe. The evidence, well, this is the evidence that we've got all these constants that are roughly right. It's a cumulative case. Difficult to put precise numbers into all of this, but cumulatively, as I said, most physicists and cosmologists are convinced that there's something there. But there's negative wishful thinking. Here's Susskind again. He says in his book, the Anthropic Principle makes many physicists very uncomfortable. The need for a supernatural agent is a threatening anti-scientific idea. Well, he's honest enough to make himself clear. He writes his book perfectly honestly, but this is just an argument against people who say, oh, you people are just thinking in a wishful manner. No, the opposite is just as much present. So here are the final thoughts. The conclusion is that it is entirely reasonable to believe that God designed the universe. And it may even be the simplest hypothesis when you look at the others. Theistic belief can accommodate multiple universes. I mean, as I said, if God wanted to do it this way, who are we to complain? None of this is a scientific hypothesis right now. That's clear. And be aware that it is sometimes rather hard to distinguish anti-religion from what calls itself philosophy. Thank you very much.